So besides WGAN, I also found another kind of GAN which is useful. It's called energy-based GAN, EB-GAN. So the special part of this EB-GAN is layer discriminator is actually an autoencoder. The training procedure of EB-GAN is exactly the same as the typical GAN. However, they modify the network architecture of the discriminator. They use autoencoder as the discriminator. So they design their discriminator in this way. So as you know, the discriminator take an image as input and it will output a scalar representing whether an image is good or not. And in EB-GAN, their discriminator is actually an autoencoder. And the reconstruction error of this autoencoder will be considered as the quality of the input image. So if an image can have small reconstruction error, means it's high quality, and if an image cannot be reconstructed, that means it has poor quality. So the discriminator defined like this way. So there is an autoencoder in the discriminator, and as you know, the autoencoder has an encoder and a decoder, and the autoencoder take an image as input, and after an encoder and a decoder, it tries to reconstruct the image. Of course, it cannot reconstruct the image perfectly. Then you can compute the reconstruction error, and this reconstruction error will be times by minus 1, and the final result is the output of your discriminator. For the other part of the GAN, how to train a generator, how to train the discriminator, is exactly the same as the typical GAN. Why I consider energy-based GAN as useful is because when you train a discriminator at the beginning, at the first few iterations, is very unstable. This is because you cannot train your discriminator pretty well, because the discriminator needs some training data. It needs some positive example, it needs some negative example. And the negative example is generated by your generator, and at the first few iterations, the generator is so poor, so it generates very poor data to the discriminator, so discriminator cannot be very powerful. Then people will consider, can we pre-train the discriminators to lead to more stable GAN training procedure? However, it's very difficult to pre-train the discriminator because your discriminator is a binary classifier. Binary classifier need 2 classes of data to train. And at the beginning, you don't have a generator, you only have positive example. So you cannot train a binary classifier with only 1 class of data. But the benefit of the autoencoder is, as you know, autoencoder can be trained with only real positive example. You only need to collect lots of real image, then you can train an autoencoder. You do not really need to generate the example to train an autoencoder. So when you use energy-based GAN, the tip is first use lots of real example. You do not have the generator, so you do not have negative example. You only have real image. Use real image to pre-train your autoencoder. To train it well, then you consider this autoencoder as the initial parameter of your discriminator. Then you train your discriminator and generator in the same way as typical GAN. So this is another good approach, which is called EB-GAN. So let me ignore some pages. So another issue when training GAN is modulus. Modulus means your real distribution is very large. However, all the generated data looks the same. On enemy phase generation, when modulus happen, it looks something like that. The generator always generates this kind of image, and this phase can have different color, but it's apparently all this. It's just the same, and it is everywhere. It usually like this enemy phase very much. So this is an issue. There's another issue which is not as serious as modulus, which is called mode dropping, means your real distribution has several modes. However, the generator can only generate some of them. So here is a real example. We train a phase generator, and at iteration t, this is the output of the generator. It looks okay, doesn't have severe problem, not modulus. But when you look at the example of next generation, you found that this generator generates these phases. Then you found that those generator can only generate the character, only generate the face with the skin with similar color. And in another iteration, it generates this kind of face. So it cannot generate the face of all the different kinds of color. This is a discrimination. So this is not a good way to train. So this is not a good thing. We have to deal with this problem. And there, of course, there are lots of approaches proposed to deal with the problem of mode collapse. But I found that there is a very, very simple and effective approach. Let's assume that your generator is mode collapse or mode drop. So your generator can only generate some very specific image. However, you train a set of generator. You train N generator. Actually, this is learned from my student because, as I have said, eminent phase generation is one of the homework of my deep learning course. And I will ask the student, say, you have to generate 25 images. Then I will give there the score based on the generation result. And if your generator is mode collapse, always generate the same image, then of course you cannot get good score. However, some students figure out that if I want them generate 25 images, they just train 25 generator. And when they have to generate an image, just randomly pick a generator and generate the image. Even although single generator mode collapse, but ensemble together, the result looks pretty good. So this is the tip to handle the problem of mode collapse. You will get, they can get full score in this way. Okay. So last, I want to talk about how to evaluate your generator, because as you can imagine, it's very hard to evaluate the generator. In my deep learning course, TA have to look at the image themselves to give the score, because there is no good automatical way to evaluate the result. So, but of course, in the literature, there are some way to automatically evaluate the result. I want to skip some few pages. I want to directly describe Inception score. So there is an objective evaluation approach called Inception score, which is widely used in the literature today. So in Inception score, you use an off-the-shelf image classifier, and because the original paper used Inception net, so they call it Inception score. If you use VGG, you should call it VGG score. But people use Inception net, so you should call it Inception score. So you use an off-the-shelf image classifier. And this classifier takes an image as input and output a class distribution. And if the generated image has high quality, then the output distribution to be concentrated on some specific class. So because the input image has high quality, so the image classifier will be very confident which class this image belongs to. So you will have a concentrated distribution. However, only evaluate on a single image is not sufficient, because it is very possible that your model is mode collapse. It can only generate a single image, but high quality. So to evaluate whether mode collapse happened, you should generate a set of image. And the off-the-shelf classifier take this image as input and generate a distribution for each image. Then you summation, you average all the distribution. You have a set of distribution, you average all the distribution, and obtain a final distribution. And you want this final distribution to be uniform. Why? Because if your generator always generates the same image, then the output distribution will always be the same. For example, it always considers the input as class 2, then after the image, it will be very balanced. The class 2 will have very large probability. However, if the output of your generator have very high variety, then all the distribution will be different. Then you summation over, you average over all the distribution, then you will have an average distribution. So the idea of Inception score is, given a single image, the output distribution should be concentrated or has a low entropy. And given a set of image and average the output of a set of image, you should have a uniform distribution. The distribution should have high entropy. Okay, so this is the definition of the Inception score. You want the output of single image to be as concentrated as possible. So you compute the negative entropy of a specific image and summation over all the image. And you want the average of the distribution to be uniform, so you compute the entropy of PY. You compute the entropy of the average of all the generated image, then you put this score together, you have the Inception score. So this score is widely used in the literature. So let's talk about conditional generation. In the previous few slides, until now, the machine can only generate random image. It takes a random vector, then generate a random image. You cannot control the output of the generation. Now I'm going to talk about how to control the output of the generation by, for example, text comment. So here, what I'm going to talk about is text to image. Input text, and the machine generate the image corresponding to the description. And this can be solved by supervised learning. You do not really need GAN to solve this problem. If you have the training data like this, you have an image, and you have the label like this is a dog running, and this is a bird is flying, something like that. You can train a neural network by typical supervised learning approach, and the network take the text description as input and generate the target image. However, the supervised learning cannot obtain good result in this application, because in your training data, for example, the description trend will appear several times, but it corresponding to different images. So this is a trend, this is a trend, this is a trend, and all these images are the trend. During the training, you want the network output image, which is close to this image, but at the same time also close to this image. Then in the end, the machine will output the average of all the different kind of trend, and the result will be poor. You will obtain a blurry image. If the machine can generate one of this image, it can probably get good result. However, machine does not know that. You tell the machine to generate an image which is similar to the reference, and you have several references. The machine can only generate the average of different kind of trend and obtain a blurry image. So if you use supervised learning, usually the output will be blurry. So this is the problem of supervised learning. Now we can use conditional GAN to have better result. In conditional GAN, you also learn a generator, and the generator takes the text description as input and output an image. And the generator also have to take a random vector sample from the normal distribution as input. Based on this text description and this Z, it will generate an output image. And the generator is not learned from a specific image. The generator is learned from a discriminator. However, the discriminator using conditional training is different from the original generation. In the original generation, we say we have a discriminator, it takes the image as output and output scalar. And this discriminator will check whether the input image is high quality or not. However, this is not sufficient for conditional GAN, because even though this discriminator can discriminate real image and generated image, it can assign large score to the real image and assign small score to the generated image. Generator, to cheat the discriminator, it only have to generate some real image, but ignore the input. You say, you ask the generator to generate a trend. Generator probably always generate a dog. If the dog is cute enough, it can cheat the discriminator, then the discriminator still give it good score. So this is not what we want, because what we want is conditional generation. So in conditional generation, you have to keep in mind that this is very important. You have to keep in mind that your discriminator takes the input and output of the generator as input. Your discriminator needs two input. It considers the condition as input. It also conditions the generated result as input and assign a score. And this score has two meanings. One is whether the generated image X is realistic or not. But at the same time, this score has to represent whether the condition and the generated result is paired or not. Okay. So if you say trend and the generator generate a dog, but the dog is pretty realistic, probably it can get some good score. However, because the condition and the generated output are not matched, so eventually the final output of the discriminator will be small. So this is the idea of conditional GAN. To train this kind of discriminator, the true data is if you have the real image and its corresponding text, then the discriminator to assign large score to it. And there are two cases the discriminator have to assign small score. One is the realistic image, but with unrelated text. Then this case, even though the image looks pretty realistic, it should obtain small score. It's very easy to generate this kind of example, you just sample from some real image and random give it some text, then you can obtain this kind of negative training example. Then another case should still assign a small score. You have text but generated image. This case should still assign a small score. So this is the algorithm of conditional GAN. I would like to skip it. And in conditional GAN, I found that you can design your discriminator and obtain different results. Usually, people design their discriminator in this way. As I have mentioned, the discriminator takes the object, the generated result, and condition as input and output as final score. So usually, people design their discriminator in this way. First of all, input an object, and you need a network to do some transform and obtain the embedding of this object. And you have the condition, and another network will transform the condition into another embedding, and network take two embedding as input and obtain the score. Because usually your object and condition are from different domain. This is image, this is the text, they are very different. So you need different network to compress them, to represent them into the embedding. Then you use a shared network to base on these two embedding and assign a score. So this is the typical way. But I found that from the literature, there is another design of discriminator seem to obtain very good result. You can disentangle the realistic and the match score. So the network can output two score, and the input is an object and a condition. Then you have a first network which take the condition X as input, and output score represent whether this object, the input of this green network is an object, and the output of this network will determine whether the input object is realistic or not. And this blue network takes the output of this green network, and the condition is input, and output whether they are matched or not. So you can disentangle the judgment of whether an X is realistic or not, and whether C and X is can be considered as a pair or not. I put some literature here for your consideration. Okay, so this is also one of the homework of my deep learning course. The student have to generate anime face based on the text description. For example, if I input blue eyes, red hair, short hair, you should generate some image face like in this way. Of course, the text to image test is supervised, so we have to collect lots of anime faces from the internet, and all the faces should have some label. We should label the characteristic of those faces. And this is the result from the student. So when I enter red hair, green eyes, this is the result. So the character has red hair and green eyes. When I enter blue hair and red eyes, this is the result I can obtain. Of course, machine sometimes makes some mistake. So look at this one. This girl has one red eye and one blue eye, so machine do not learn that two eyes should have the same color if think one red eye is good enough. And to get the best result, you can use StarGAN. The idea is very simple. Based on the text description, you first generate a small image, and based on the small image, you generate a larger one. So I'm not going to go through the detail of this one. So we have just mentioned text to image. Of course, you can do something like image to image. You can transform this kind of simple image into a realistic house. And there are lots of occasions. For example, you can transform a black white image into a colorful image. You can transform the day into night, something like that. So this is how you do that. As I have mentioned, conditional generation can be trained by typical supervised learning. So if you have some pair training data, of course, you can apply traditional supervised learning. You can learn a network, input this image. The output should be as close as possible to this realistic house. However, the result is something like this. So as I have mentioned, typical supervised learning usually yielded blurry image, something like that. So you need GAN. So you need a generator. Generator take the condition and a random vector as input and generate an image. Then you have a discriminator. Discriminator take the input and output of the generator. So I have emphasized this several times. If you want to train the conditional GAN, your discriminator should take the input and output of the generator as input and obtain a score. And with the GAN, you can obtain the result like that. But the result is not perfect because you can find that here there's a window on the roof. So the machine adds some weird thing which is not appear in the original input image. So to prevent this happen, there is another way. You can put another constraint. The constraint is the generated image cannot be very different from its ground truth. Because it's supervised learning, actually you have the ground truth. You know these two images are paired. So you can put a constraint that the generator not only have to cheat the discriminator, however, at the same time, the output image should be close to the ground truth. So with this constraint, the result is something look like this. So let's skip this one. And of course, conditional GAN can be used in image super resolution. I believe you have seen this kind of example so many times. So for super resolution, you just train the conditional GAN, input blurry image, then output clear image. That's it. For image completion, just use exactly the same technology. Input the image with some holes, and the conditional generator will output the complete image. And you can find some demo on the internet, so you can check it by yourself. So you can just check the link by yourself because I know you have the slides. This is another application. You can do video generation. So you train a generator. The input is the first few frames of the video, and the output can be the next frame. So you train a discriminator. As I have mentioned, this is probably the 4th time I've mentioned this. For the discriminator, you have to take the input and output together as the input. So the generator take the first few frames as the input and output the next frame. Then you concatenate the input of and output of the generator as the input of the discriminator. And the discriminator will check whether this video is realistic or not. And this is a video I found on the internet. Someone used GAN to generate the video GAN of Pac-Man. And the rightmost image are the result without adversarial training. And you can find that without the adversarial training, sometimes the Pac-Man will split. The Pac-Man will split at the corner. Let me find an example. For example, here or here, it will split. So why the Pac-Man split? Because in the training data, at the same corner, sometimes Pac-Man turn left, sometimes Pac-Man turn right. However, the machine do not know that. As I have said, if you have two ground truth, machine will learn the average of these two ground truth. So the Pac-Man will turn left and turn right at the same time. So turn left is good, turn right is good, but turn left and turn right at the same time is bad. But machine do not know that. With GAN, machine do not learn from a specific example. It learns from the discriminator. So you can find that with the GAN, the Pac-Man will not split. But of course, sometimes it still get bad result because some Pac-Man suddenly disappear. And I also found that the digit is changed, but is changed in a random way. So for feature extraction, GAN can be used in feature extraction, but due to time limitation, I would like to focus only one technology, which is domain adversarial training. So you can check the slide yourself. Here we have InfoGAN. Here this technology proposed by NVIDIA. They have a very cool demo. You can check the video yourself. And some people use the technology to develop intelligent Photoshop. You can check the video yourself. So what I only want to talk about is adversarial training, domain adversarial training, because it will be very useful in the following talk. And GAN can be used jointly with VAE. So this is VAE GAN. GAN can be used in train an autoencoder. This is called by GAN. Another interesting fact is there's another technology called ALI, and by GAN both published at iClear 2007, and they do not have any difference. They are exactly the same, but with different name proposed by different people. Okay, so the only thing I want to talk about is domain adversarial training. So usually, sometimes your training data and testing data came from different domains. And everyone is the expert of machine learning, so you know that if your training data and testing data from different domains, they have different distribution. Training on the training data will not work well on the testing data. So if you train your classifier on black and white NIS and test them on colorful NIS, you will get bad result, even though the digits are just the same. So the idea here is learn a generator. This generator is actually a feature extractor. Take an image as input, it output a vector. It output a vector for the classifier. And using this generator, it will remove the domain difference. It will remove the domain dependent factor. So given an image from here, given an image from here, the output feature will have the same distribution. So the target here is learn a generator. Given the object from different domains, the output feature will have the same distribution. The basic idea is look like this. You have a feature extractor, or you have a generator, input an image, input an object, and output is a feature vector. And you have some image from domain A, you have some image from domain B, but after this feature extractor, the output of domain A and the output of domain B have the same distribution. Let's assume those image corresponding to blue point, those image corresponding to red point, and you want this two set of points have the same distribution. To achieve that, you need a domain classifier or a domain, or actually a domain, you need a discriminator. So this domain classifier is a discriminator. The job of this discriminator is to determine, given this feature, it belongs to which domain. And this discriminator will learn to judge whether this feature belongs to domain A or domain B, and this feature extractor will try to cheat the discriminator, will try to cheat the domain classifier. If this feature extractor successfully cheat this discriminator, cheat this domain classifier, then the image from different domains have the same distribution. However, for the feature extractor, it's so easy to cheat the discriminator because it can always output zero vector. No matter the input image is, it always output the zero vector. Then the domain classifier do not have any information to discriminate an image is from which domain. Then it fail, but the result is not what we want. To deal with this problem, you need another classifier. This is a label predictor. So now the generator has two jobs. The first job is its feature should cheat the discriminator. Its feature should cheat the domain classifier. Domain classifier cannot get any domain information from this kind of feature. However, at the same time, this generator should also help the label predictor. The label predictor should be able to get correct label from this feature extractor. So in this approach, by this training approach, this feature extractor can generate a feature which removes the domain dependent feature but keep the label feature. So it can get good result from the label classifier, but it can cheat the domain classifier. And this approach is successfully applied on image classification. Then in the following talk, we will show some good results from speech and text-related application. So this is some result from the literature. Of course, it get good results, so we skip this page. So then let's talk about unsupervised conditional generation. We already talked about conditional generation, but we mentioned that conditional generation is supervised. You can directly use supervised learning approach to train a conditional generator, but it may not get good result. You should involve a discriminator to get good result. However, conditional generator can be trained in an unsupervised way. This is very amazing. You want to train a generator to transform an object in the X domain into an object in the Y domain. But you do not need paired data in X domain and Y domain. You only have to collect the image in X domain and collect the image in the Y domain. Then that's it. You can learn a conditional generator without paired data. And this technology can also be used in speech and text processing. We will see some example later. And now let's focus on image. So suppose that you have some real photo and you have some painting of Van Gogh, then you do not need paired data between Van Gogh's painting and the real photo, or actually this kind of pair data doesn't exist, and you can train a generator without pair data. So this is how people achieve that. There are two categories of approach. One is directly transformation. You learn a generator which can directly transform an image from X domain to Y domain. And empirically, I found that this approach is most suitable to do small transformation. It usually, on image processing, it can only change the texture or the color of the input image. It cannot do very large training. It cannot change the structure of the input. And another approach is projecting the data from different domains in the same space. In the second category, you can do larger modification. For example, this is not a real example. If you want to transform a real profile into cartoon style, this is the approach you can use. And so to use this approach, you need to train an encoder of domain X. Then this encoder will extract the face attribute from the input image. And you have a decoder of domain Y, which is another kind of face. And this decoder of domain Y generates an image based on the input attribute. With this approach, it's more easier to make the input and output very different. So let's talk about the first approach. So in the first approach, let's assume we have some image from domain X, which are real image, which are photos, and you have some image from domain Y, which are the paintings of Van Gogh. Then you train a generator, input a photo. We want it to output another image, which look like the painting of Van Gogh. To achieve that, you need a discriminator. You need a discriminator of Y domain. This discriminator is provided by a lot of painting from Y domain, so it knows the image, what the image in the Y domain looks like. So it outputs a scalar. This scalar represents whether the input image looks like the image in Y domain or not. And as I have mentioned, the generator will try to cheat the discriminator. So if the generator successfully folds the discriminator, means the output image looks like the image in Y domain. However, this cannot completely solve the problem, because it is very possible that the generator just generates an image looks similar to the image in the Y domain, but completely ignore the input, not related to the input. So it can generate a profile of Van Gogh, which look like exactly the same as this image, so the discriminator cannot find the difference between this, so give a high score. However, it ignores the input. This is definitely what we want. And there are several ways to solve this problem. The first idea is just ignore this issue. This issue do not really happen frequently. So based on the literature, I put the reference here. In an iClear paper, people found that if your generator is not very deep, then the input and output usually look quite similar. The generator cannot make too much difference. The input and output of the generator, if you do not put too much constraint, the input and output of the generator usually looks similar if your network is not very deep. So this situation do not frequently happen. It's not easy for a generator to transform this photo into the profile of Van Gogh. So probably you do not have to worry about this issue. This is the first solution. The second solution using the baseline of domain transfer network is you have another off-the-shelf classifier. You have another pre-trained network. For example, you have VGG. And given an image, VGG will extract its semantic feature. And we want the semantic feature of these two images to be as close as possible. So if this generator generates a Van Gogh's profile, this image and this image cannot have the same semantic feature. If this encoder network is good enough, if, for example, this is a VGG, if the VGG is good enough, then given this very different image, the output will be very different. And during the training, you want the output of the encoder take these two images as input and output two vector. And you want these two vectors to be as close as possible. This is another training criterion. And this will keep the input and output image to not be very different. Another way, which is widely used, is CycleGAN. You put another generator, so your original generator transform an image in X domain into Y domain. Then you have another generator transform the image from Y domain back into the X domain. And during the training criterion is you want the input image after transform 2 times still be the same as the input image. So you transform this image into Van Gogh painting, and after another transformation, it should be back to the original image. So to make the input and output as close as possible, the first generator cannot generate Van Gogh painting. Because if the first generator generates Van Gogh painting, the second generator do not have sufficient information to reconstruct the original image. So during the training, this will not be happen. So this is called cycle consistency. So you want the input and the output to be as close as possible. This is called cycle consistency. And this approach is called CycleGAN, and CycleGAN can have 2 paths. One path is you first transform X domain to Y domain back to X domain. And you can also transform an image from Y domain to X domain and from X domain back to Y domain. You also need a discriminator of X domain to verify that this image is belong to X domain or not. And you also need cycle consistency to make sure the input and output is as close as possible. And this is so someone used this technology to transform the enemy faces into silver faces. And it's pretty easy for CycleGAN to achieve that, because I have mentioned that CycleGAN is good at transforming the texture and or the color. So I'm not surprised about the result. What I'm surprised is someone likes silver hair so much. Yeah, so transform any color into silver hair. And besides CycleGAN, there are another technology very similar to CycleGAN. One is StarGAN, one is discoGAN. What is the difference between these 3 GAN? Actually, they don't have difference. They are the same, and proposed by different groups at the same month and published in different conference. But the technology is the same. So for StarGAN, you just transform from domain X to domain Y. So if you have several different domains, you need several generators. However, there's another technology called StarGAN. So for CycleGAN, you need a generator for each pair. For StarGAN, you only need 1 generator, but can be transformed between different domains. I'm not going to go through the details of this technology. So I already talking about the first approach. You directly learn a transformer from X domain to Y domain. You train a generator from X domain to Y domain. Then let's talk about the second approach. In the second approach, you have an encoder for X domain. Then you have an decoder for Y domain. So the basic idea is look like this. We have 2 domains. One is real photo and another is enemy faces. Then you have the encoder of X domain and encoder of Y domain. You have the decoder of X domain and decoder of Y domain. Then when you input an image from the X domain, you use the X domain encoder to extract its face attribute. So the output of this encoder is a vector, and we can assume that each dimension corresponding to a specific face attribute. Then you use the decoder of Y domain to reconstruct an image based on this face attribute. And because the image of this face attribute is something like a male and with glasses, so probably the output of the decoder will be something look like that. So you successfully do the domain transformation. So this is the basic idea of the second approach. However, during the training time, because we do not have the paired data, if we have the paired data, it's very simple. You can say input this image, and this is what we want. However, we do not have any paired data. We only have a pile of data from X domain and a pile of data from Y domain. So to train those encoder, to train those decoder, what you can do is train the encoder and decoder by the idea of autoencoder. So input this image, encoder extract the feature, and the decoder decode the original image. The decoder decode the input image. And of course, you want to minimize the reconstruction error, just simply as training autoencoder. And input this image, then extract the feature, and the decoder will decode the same image. Of course, you want to minimize the reconstruction error. And as I have mentioned, if you only train your decoder or your generator by minimize the reconstruction error, as in VAE or autoencoder, you will usually get very blurry image, so you need a GAN. So you need a discriminator. So you have a discriminator of X domain. Discriminator will make sure this image look like the image in X domain. And you also have a discriminator in Y domain. The discriminator in Y domain will make sure this image looks like image in Y domain. However, only train this 2 encoder, 2 decoder, and 2 discriminator is not sufficient because the 2 encoders are trained separately, right? So you input an image, it reconstructed at here. You input another image, it reconstructed at here. And this 2 encoder may not share the same space because probably the encoder X use dimension 1 to 5 to encode the image, and this encoder Y use dimension 6 to 10 to encode the image. So if you say you use this encoder to obtain the face attribute and this decoder to take this image as input, you may not generate the image you want. Probably you input this image and this face attribute, this vector distribution say, this attribute say this is male with glasses. However, this decoder do not know that, right? This decoder can successfully generate the original image. However, this decoder is trained separately from this encoder. So it does not know the meaning of this vector. So it will probably just generate another completely unrelated image. So to deal with this problem, you need further constraint. You need further constraint to make sure that these 2 encoders encode the face attribute in the same way, encode the face attribute in the same space. So there are several approaches. One approach used in couple GAN and unit is you tie the parameter of this 2 encoder. You tie the parameter of this 2 decoder. Usually you will tie the parameter of the last few layers of the encoders, and you will tie the parameter of the first few layers of the decoder. And because the parameter is tied in the last few layers, so you can imagine that probably this 2 encoder will use the same way to encode the last attribute because their last few layers has the same parameter. So probably they use the same way to encode the face attribute. This is one approach. Another approach is borrow the idea of GAN, actually borrow the idea of domain adversarial training. You train a domain classifier, and this domain classifier has to discriminate whether a vector is from X domain, from the encoder X, or from Y domain, or from the encoder Y. And the domain classifier has to discriminate whether this vector is from encoder X or encoder Y. The encoder X and encoder Y will try to fool the discriminator. If the encoder X and encoder Y successfully fool the discriminator, this means that encoder X and encoder Y will use the same way to encode the face attribute. So the discriminator cannot discriminate the difference between encoder X and encoder Y. So this is another approach. There are further other approach. For example, you can apply cycle consistency. So input this real photo and use encoder X to extract the attribute, then use decoder Y to generate an enemy faces. Then your encoder Y take these faces as input, then use encoder Y to extract the face attribute and use decoder X to generate the image. And you want this input after a cycle to be obtain the output, and you want this 2 image to be as close as possible. This idea is used in combo GAN. And if you consider carefully, the idea of, so the cycle consistent here is very similar to CycleGAN, right? Because in CycleGAN, you transform from X domain to Y domain and transform from Y domain back to X domain. You want the input and output to be as close as possible. So here, this is the generator from X domain to Y domain. This is the generator from Y domain to X domain. And you want to minimize the reconstruction error. So this idea is exactly the same as CycleGAN. The only difference is these 2 encoders have shared hidden layer. And CycleGAN, the 2 generators are just independent. There are other ideas. For example, people use semantic consistency. So semantic consistency means you use the encoder X to encode this face into face attribute. You use decoder Y to reconstruct an enemy face. And this new enemy face after encoder Y to have the same face attribute. And this is another way to force the encoder X and encoder Y use the same latent space. And this idea is used in domain transfer network and XGAN. So this is all kind of different idea about unsupervised conditional generation. We spend lots of time talking about unsupervised conditional generation because it will be widely used in my research in the last part. Then last but not least, for the general introduction of GAN, I want to connect GAN with the reinforcement learning. And probably not all the audience are familiar with reinforcement learning, so I will use a few slides to quickly introduce reinforcement learning. So in reinforcement learning, you have an actor, you have an environment, and you have a reward function. For example, when playing video game, the actor have to control the button. And the environment is the machine you play with. And the reward function is something like killing a monster, you get 20 score. And in Go, an actor is AlphaGo, your environment is another human, and the reward function is the rule of Go, something like that. And in reinforcement learning, your environment and reward function should be fixed. It cannot be modified. You cannot change it. You have no way to modify your reward function and your environment. What you can do is tune the parameter of actor to maximize the reward the actor can obtain from the environment. Then usually your actor is a neural network, and the network take an image as input. If you use the actor to play the video game, then this actor is a network. It takes the image as input, and the output is the action it should take. So if there are 3 possible actions, turn left, turn right, and fire, then the last layer of the network will have 3 neurons. And given an image, this 3 neurons will output 3 values. And for example, it outputs 0.7, 0.2, and 0.1. And we consider those values are the score of the action, and you will sample the action being taken based on this distribution. For example, you have 70% to turn left, 20% to turn right, and 10% to turn left, based on this example. So I will quickly use plain Atari GAN to describe the interaction between environment and the actor and the reward function. So at the beginning of the GAN, the actor will have an observation, which is the image of the video game, and the actor will decide to do something, for example, turn right. Then it will, after it take an action, it will obtain the reward from the reward function. Then the actor will have another observation. Based on the new observation, it will take another action, for example, fire. Let's assume it kills a monster, then it will obtain some score, and so on. So the interaction will continue until the GAN is ended based on some rule, and each GAN is considered as an episode. And what actor have to do is maximize the total reward obtained in the whole episode. You can update the parameter of the actor. The actor is a network, so you update the parameter in the network to maximize the reward can be obtained in the GANs. This is another way to simplify the interaction between actor, environment, and the reward. Environment output an image, output a state, output an observation, and the actor take the image as input, then take an action, determine an action. Then the environment take the output of the actor as input and generate another image. And the actor based on the new image and take another action. And the interaction will continue until the end of the GAN. And if you collect those image and those action together, it forms a trajectory. Then there's the reward function. Reward function take the state and action as input and provide a reward to the actor. Then you want to sum over all the output of the reward function. You want to sum over the output of the reward function over the timestamp and obtain the total reward. And the reinforcement learning is to update the parameter of the actor to maximize the total reward you can obtain in the end. And you can consider the actor as the generator and the reward function as actually as the discriminator. So remember that when we train the generator, we fix the discriminator and update the generator to obtain the maximum output from the discriminator. So here for reinforcement learning is actually the same, right? The here is fixed reward function, and you want to update your actor to obtain the largest output from the reward function. So it's actually the same from the GAN. So you can consider your reward function as the discriminator and your actor as the generator. But there is something different. First of all, in GAN, your reward function, in reinforcement learning, your reward function is fixed. In AlphaGo, the rule is fixed. For Atari GAN, the rule is fixed. So reward function is always fixed. However, in GAN, the discriminator is always changed. The discriminator will update its parameter. So in each iteration, the parameter of discriminator is different. So it looks like GAN is more challenging than reinforcement learning because your environment, your reward function is changed over time. And another different thing is in reinforcement learning, your reward and your environment is considered as a black box. So you do not know the parameter in the reward function or environment. Actually, they are not networks, so they do not have something like a parameter. And you do not know what is happening in the environment. You do not know what is happening in the reward function. However, in the GAN, the discriminator is a network, so you can do backpropagation. You can tune your parameter. You can tune the parameter of generator to maximize the output of the discriminator easily by backpropagation because you know the parameter of discriminator. In reinforcement learning, you do not know the parameter of reward function, so you cannot directly optimize your actor. You want to maximize the output. You cannot directly use backpropagation to learn the parameter of your actor. So from this point of view, reinforcement learning is more challenging than GAN, but you can find that they are actually pretty similar. There is another technology called imitation learning, which is exactly the same as GAN. So in imitation learning, the environment and the actor can still interact with each other. However, reward function is not available. Without the reward function, the actor can still be learned. The actor is learned from the demonstration of the expert. So you collect the demonstration from the expert, and you collect some trajectory from the expert, then you use this demonstration to train the actor. And for example, if you want to learn a self-driving car, then this demonstration is probably the recording of human driver. And if you want to learn, let's say, a robot, then this trajectory is human grab the hand of the robot to do something. So this is imitation learning. In imitation learning, a famous technology is called, a representative technology is called inverse reinforcement learning. In the original reinforcement learning, you have environment, you have the function, then you learn an optimal actor. However, inverse reinforcement learning is the inverse of, it's just the inverse of reinforcement learning. So now you have the demonstration of the expert. It can be considered as the optimal actor. You have the environment. Based on this information, you can learn a reward function. Then after you learn a reward function, you can, based on this reward function, to learn another optimal actor. So this is the idea of inverse reinforcement learning. So you can consider inverse reinforcement learning as the technology to find the optimal reward function. Because sometimes your reward function is not easily available. Because when you do something like training a self-driving car, you don't know what a reward function look like because you do not know whether if the car hit a human should be -100 and hit a dog to be -10, something like that. It's very hard to define this kind of reward function. So you need some technology to learn the reward function. The whole learning scenario, the whole learning procedure is look like this. So you have an expert. The expert has some demonstration, and you have your actor. The actor also interact with the environment, so you can also collect the trajectory of your actor. Then the basic idea is the expert is always the best. So you learn a reward function R, and this reward function will learn to assign larger score to the expert's trajectory and smaller score to the trajectory of the actor. So you will learn this object. You will learn this reward function to assign larger score to this object, smaller score to this object. Then you have a reward function. Then your actor will interact with the environment to maximize the reward it can obtain from this reward function. So this can be done by reinforcement learning. So after some interaction, this actor will be better at this reward function and can obtain larger reward. However, However, this reward function will be updated. So the actor know how to obtain large reward from this reward function, probably even better than its teacher, probably even better than the expert. Then the reward function will be updated. Then the actor will be very angry. And even though actor can do a good job on the original reward function, the reward function will be modified to give the actor small score. And in this scenario, the actor is actually the generator. The reward function is actually discriminator. Let's review what we have done in GAN. In GAN, you have some real image, you have a generator generate some fake image, then you have a discriminator give high score to real image and low score to the fake image. And the generator try to cheat the discriminator to generate better image. And the discriminator will also update it. Actually, it is exactly the same as reinforcement learning, inverse reinforcement learning. We just changed the name of the module, right? We just changed the name of the module. Here we have the trajectory generate from the expert. We have the trajectory generate from the actor. Then you learn a reward function to assign large score to the trajectory of the expert and small score to the trajectory of the actor. Then the actor learn to obtain large reward function from the large reward from the reward function. Then reward function will be updated to still give the large score to the expert. So inverse reinforcement learning and GAN are actually the same. We just change the name of the modules. So that's it. So let's talk about, probably we can answer some question if there's, okay, let's try to answer some question. How to use Inception score to the enemy character? Did you gather the class and train the Inception? Unfortunately, we cannot use Inception score on enemy character. So to apply the Inception score, there's still another limitation is it should be the image trained on Cypher 10, something like that, or on ImageNet, then you can use Inception score. So for enemy character, I still do not find a good way to evaluate it. In my class, I will use an enemy face detector to evaluate the result. So if your face cannot be detected by an enemy face detector, means you do not generate a good enough. Your generated face is good enough. So this is one way we evaluate the result of the student. But eventually, we still need TA to look at all the image to make sure that the result is fair, or the student will be angry. When evaluating generator with Inception, since the generated image lie in very low dimension distribution, the class distribution must be non-uniform.
That's me actually.
Okay.
There's a more question, but since like lack of a character, I didn't put the question.
Oh, okay.
I think that for like evaluating the GAN with the Inception, so you put the generated image to the Inception network and then get the class distribution. But I think since the generated image, let's say the enemy character image, they're really in the low dimensional distribution. So I thought that class distribution must be not the uniform, but some kind of
yes, yeah.
So is it really fair to use that Inception score as evaluating?
I do not really get the question. You means because the good image will get a non-uniform score, and the poor image will get the score probably more uniform. This is the assumption. So I'm not really get your question, because here we use the Inception score in two ways. One is just evaluate a single image, and another case is evaluate a batch of image, and you will combine these two scores together. And in the single image case, we want the output to be very sharp. Sharp output means good result. And I think that when you train a network, when you train the Inception net, the realistic image, which is lie on the manifold of the image, should get the sharp distribution. But for those images not lie on the manifold of the real image, the Inception score probably will give a uniform distribution. So if the generated result not on the manifold of the real image, it should get uniform distribution. Are dual GAN, CycleGAN from the same group? Oh, okay. So dual GAN, CycleGAN, and disco GAN, they are the same. by different group and but proposed in the same month. So you can look at the paper carefully. They are just the same. Okay, so here I want to talk about some the application of GAN on speech processing and natural language processing. And I determined to talking about natural language processing first, then speech processing, and we will skip speech processing if we do not have sufficient time, because natural language processing is kind of different from typical GAN. So we have to mention it. So in natural language processing, what we want to do is sequence generation. We want to generate a sequence of words. And word sequence generation has lots of application. For example, in ASR, you need to generate a sequence word given the input signal. For translation, you want to generate a sequence of word given the input language. And in chatbot, you generate a sequence word given the input sentence. So word sequence generation is very important in natural language processing. So here we are going to use the technology of GAN to improve word sequence generation. And as you know, those generators are conditional generators. Given the condition, they generate word sequence. And those generators, the network structure of those generators can simply be sequence-to-sequence model. Because I believe everyone in this room are familiar with sequence-to-sequence model, and you know sequence-to-sequence model can solve lots of natural language processing problems. It can be used in speech recognition, it can be used in machine translation, it can also be used in chatbot. But typical sequence-to-sequence model are trained by maximum the likelihood. But with GAN, you do not have to train sequence-to-sequence model by maximize the likelihood. You can train sequence-to-sequence model with different approach. This is what we want to point out here. So let's first take a look at the problem of maximum likelihood. Let's suppose you want to train a chatbot, and this is your generator, and it has an encoder, it has a decoder, and input a sentence, it should output the response. Then to train the chatbot, you need some training data. Your training data look like this. When A say, how are you? The response of B is I'm good. Then the generator will learn that when input how are you, the reference output is I'm good. The typical way to train a sequence-to-sequence model is maximize the likelihood, but of course it's not a good idea because let's suppose there are two possible responses. One is not bad, one is 안녕. For human, if you say how are you, response with 안녕 is ridiculous, not bad is okay. So for human, this is better. But for maximum likelihood, 안녕 is actually better because at least it has one word the same. It has 50% correct, and response with not bad is totally wrong. So if you try to maximize if you try to train your model to maximize sequence-to-sequence model, probably when input how are you, the machine will output 안녕. Of course, this is not a good result. To deal with this problem, there are two directions. One is reinforcement learning. In reinforcement learning, we use human feedback. Then in GAN, we use discriminator to provide the feedback. I will first describe reinforcement learning, then GAN, and you will find that reinforcement learning is a special case of GAN. So here is the introduction of reinforcement learning. So if you want to use reinforcement learning to train the chatbot, here is the scenario. So when someone say, how are you? The response of the bot is bye-bye. Then human will be angry and give a negative reward. And if human say hello, the bot say hi, then the result is good, so positive reward. And the chatbot will learn to maximize the expected reward. So here is your chatbot. It's an encoder-decoder architecture. It's a sequence-to-sequence model. Input a sentence, it output a response. Then here is a human. Actually, human is another function. The human take the input sentence and output response as input and give a score. Say, when input is how are you, response with bye-bye, how bad it is. So given two sentences, given the input sentence and the response, human provide a score. This is the reward. And the target of the chatbot is learn to maximize the reward from the human. And to learn to train this chatbot, to train this sequence-to-sequence model, the typical technology is policy gradient. I'm not going to go through the formulation of policy gradient. It is kind of complicated. Let's just talk about its result. So how to implement policy gradient. It's very intuitive. You implement like this way. You have a chatbot with parameters theta t, and it interact with the human. So when human says C1, chatbot respond with X1, then the human give a score. When human says C2, chatbot interact with X2, then give another score. So interact with N time, so you have N pairs of data, you have N score. Then you have to update the parameter to maximize the possible reward, to maximize the expected reward. How to update your parameter? We are not going to go through the detail. Just keep in mind that in policy gradient, you update your parameter by this formulation. So this is the formulation. So kind of complicated. We do not describe it. But the basic idea is if Ci and Xi, this pair of input and response, obtain positive reward, then the parameter will be updated to increase the probability of generating X given C, to increase the probability of generating Xi given Ci. And if pair Ci, Xi obtain negative reward from the human, then the model will update the parameter to decrease the probability of observing Xi given Ci. So this is very intuitive. If this pair is good, if this response is good, then increase its probability. If this response is bad, obtain negative reward, then decrease its probability. That's it. This is the basic idea of policy gradient. And you can compare reinforcement learning, actually policy gradient, with maximum likelihood. In maximum likelihood, you have a set of training data. We will tell the machine that input C1, the optimal response is X1 hat. Input Cn, the optimal response is Xn hat. Then you train your sequence-to-sequence model to maximize the likelihood. Your objective function is look like this. You want to summation over all the training data, and you want to maximize the log probability of X hat given C. You want to maximize the log probability of Xi hat given Ci. And your gradient looks like this. This is very simple. Then you can compare maximum likelihood with reinforcement learning, and you will find that it's very intuitive. So your training data in reinforcement learning, your training data look like this. When human says C1, then the machine responds with X1. When human says Cn, the machine responds with Xn. Those response X are not provided by human. They are generated by machine. And your gradient look like this. Your gradient look like this. And based on this gradient, you can infer that the objective function of reinforcement learning is look like this. So this objective function is actually pretty intuitive. Summation over all the training example you get, and you want to maximize the log probability. You want to maximize Xi, the probability of Xi given Ci, but this log probability is weighted by the reward. So if a pair of Ci, Xi obtain positive reward, increases probability. If a pair of Ci, Xi obtain negative reward, decreases probability. This is very, very intuitive. So the difference between maximum likelihood and reinforcement learning is that in maximum likelihood, all the examples simply weighted by 1. In reinforcement learning, all the examples are weighted by its reward. Actually, it's pretty easy to implement reinforcement learning. However, humans are very busy. No one can interact with the machine for millions of times. So some people figure out an AlphaGo style training. Just let two agents talk to each other. One say, how are you? Another say, see you. He says, see you. And he says, see you. Then they will never stop. And sometimes it still get good result. And however, they are both machines. So they do not know that stuck in see you loop is a bad idea. They do not know that. So you need to have a handcrafted function. This handcrafted function will tell the machine that this situation is bad, this situation is better, then give the feedback to the chatbot, so the chatbot can be learned. But this is not the best idea because you do not know how to define the evaluation function. You cannot develop very sophisticated evaluation function. So then we can use GAN. In GAN, the idea is very simple. This is your chatbot, just as is exactly the same as what you do in reinforcement learning. But now we do not involve human. We replace human with the discriminator. So the discriminator also takes the input and the output response as input and output a score. And what the discriminator do is it will determine whether this pair, looks like the generated pair from the chatbot or look like the same as the human dialogue, and it will provide a score. And you can consider that in original reinforcement learning, we use human to give the feedback. Now in reinforcement, now in GAN, when we use GAN, we use discriminator to give the feedback. So we do not have to involve the human. So this is the algorithm of using the GAN to train the chatbot. So you initialize your generator, a sequence-to-sequence model. Then you initialize your discriminator. You need some training data. The training data is pairs of conditional input C and the response of X. Then in each iteration, you sample some real data. You sample some real C and X pair from the training data. Then you also need to generate some data. You sample some condition C plane, and based on C plane, you generate a response X tilde. Then you train your discriminator. The discriminator will give the real example pair larger score and the fake example pair smaller score. Now the critical part is how to train your generator. Because what you want to do is in the original idea of GAN, you will concatenate your chatbot and the discriminator together and try to update your chatbot to maximize the output of the discriminator. This is the basic idea of GAN. However, you cannot do that in this situation. In text generation, you cannot train your generator and discriminator jointly. You cannot concatenate your chatbot and discriminator jointly in, when you are working on natural language processing. So this is the reason why you cannot do that. So here you have a sequence-to-sequence model. Okay? So this red vector is the embedding from the encoder or extracted by the attention mechanism. And based on this vector, your decoder will generate a word distribution. And based on this word distribution, we will sample a word from this distribution. So the first word generated by your sequence-to-sequence model will be word B. Then your decoder will take the generated word as input, and based on probably from the attention mechanism, generate another distribution. Based on this second distribution, we will sample another word. Probably this time, the sample result is word A. Then in the third time, sample another word, which is word A. So theoretically, what we want to do is discriminator take the output of the generator as input. The discriminator take the output of the generator as input and output a scalar, represent how good the input sequence is. Then you want to update the score to maximize the output of the discriminator. You want to update your generator, which is a sequence-to-sequence model, to obtain the maximum output from the discriminator. However, you cannot do that, or you cannot simply use gradient descent or gradient ascent to solve this problem, because when you do backpropagation, you do backpropagation from here, from the discriminator back to the generator, you will be stuck at the sampling process. So, or the simplest explanation is try to implement this kind of network by yourself. You will get some error. It will not work. So this sampling process is not differentiable. So if you consider your sequence-to-sequence model and your discriminator jointly as a large network, there is a sampling process in your network. When there's a sampling process in your network, you cannot directly train it by backpropagation. So you cannot directly train your generator to maximize the output of the discriminator, because this network is not differentiable. So there are three categories of solution. The first one is compare softmax. Not too many people use it, but it's useful, but not many people use it. So I'm not going to go through the details of it. It's kind of like VAE. So it also use reparameterization trick, and I just left some web page here. You can learn it by yourself. Then the second approach is just give the discriminator continuous input, because we say that if there is a sampling process, then you cannot directly train the generator. Let's ignore the sampling process. So the input of the discriminator is not the sampled word. It's with the discriminator directly take the distribution as input. In this way, because you ignore the sampling process, the generator and the discriminator can be jointly learned. You can use backpropagation to update the parameter of your generator to maximize the output of the discriminator. However, the issue is like this. As you know, each word can be represented by a one-half vector. And the discriminator has to discriminate between the real sentence and the generated sentence. Now the problem is your real sentence always look like this. Each word is represented by a 1/2 vector. So all the real sentence look like this, look like this. And all the generated sentence look like this. It's not 1/2 vector because the output of your decoder is a distribution. Then for the discriminator, it can easily find the difference between the real sentence and the generated sentence. It will not consider for the semantic of the sentence. It just need to consider the distribution of each vector. Then, because the generator knows that your discriminator used the distribution to judge its performance, then the generator will not consider the semantic. What it will do is it just quickly generate some very sharp distribution. Hopefully, it can cheat the discriminator. However, the generated sentence is just meaningless because the generator will not consider the semantic. It's more easier for the generator is quickly generate a 1/2 vector to cheat the discriminator. So this idea doesn't really work. There's one way to make this idea work is use WGAN. Because in WGAN, you put some constraint to the discriminator. So your discriminator will not easily judge the difference between these two situations because you have some constraint like one this is function. So the discriminator cannot easily tell the difference of these two situations. So with the WGAN, you can use continuous input to train sequence-to-sequence model, to train sequence generation. The last approach is reinforcement learning. So the idea is like this. Consider your output of your discriminator as reward. So your discriminator is the environment. Consider its output as the reward. Then we say we want to update our generator to cheat the discriminator, to fool the discriminator to get the optimal reward. This is equivalent to in reinforcement learning, you want to train your agent to obtain the maximum reward from the environment. So just consider your generator as an agent, your discriminator as the environment, then directly apply the reinforcement learning technology. Apply the reinforcement learning technology you know, and you can train generator in the scenario of GAN. So that's it. You can use any reinforcement learning technology you know. For example, if you think actor quit is good, you can just apply actor quitting. In Ian Goodfellow's sequence generation paper, he do apply actor quitting. So this is the whole scenario. So we have said that in reinforcement learning, so this is the scenario of reinforcement learning. So your chatbot and the human talk to each other and obtain some reward, and based on this reward, you will update your parameter. This is for reinforcement learning. For GAN, the only thing you have to do is replace this human with the discriminator, which is another robot. And this discriminator take a pair of input and response, and as input, you take this one and obtain a score. So originally, it's reward from the human. Now it's the score from the discriminator. Also can be considered as another kind of reward. For the formulation here, for the formulation of update your parameter, what you only have to do is replace the reward R function here with the D function. That's it. So if a pair obtain positive D value, then increases probability. A pair obtain negative D value, decreases probability. That's it. So this is how we train the generator. But in GAN, you do not only train the generator, you also train your discriminator. So you train your discriminator in this way. So your discriminator will have some fake data generated from the chatbot, from your sequence-to-sequence model. Then you also sample some real data from the real human dialogue. And you use real data and the fake data to train the discriminator. After you train your discriminator, then you train your generator by this approach, by the interaction between the chatbot and the discriminator. After you train your chatbot, then you can train your discriminator. You conducted this step and this step iteratively. So this is how you apply GAN on sequence-to-sequence model. We are running out of the time. So I will not go into describe this few page. The take-home message is it's not that easy to get it work because, as you know, reinforcement learning is hard to train. But there are lots of different tips in reinforcement learning. So apply those tips on your GAN sequence generation test. For example, people will use something like Monte Carlo search. As you know, in AlphaGo, DeepMind use Monte Carlo search. So actually in sequence generation, you also use Monte Carlo search, something very similar to the training procedure of AlphaGo. So apply any reinforcement learning technology you know on the sequence generation by GAN. And this technology is not only used in chatbot, people also use in machine translation, abstractive summarization, and caption generation. So the take-home message here is if you are working on sequence-to-sequence model, you can also consider improve your sequence-to-sequence model by GAN. For this page, what I want to say is you can also working on unsupervised sequence-to-sequence learning. You will see more example in part 3. Here, this example is from Facebook. They published 2 papers in iClear 2018. So the basic idea is we already know how to do unsupervised conditional generation, right? You can transform from real photo to the painting of Van Gogh. Then, you just simply consider, for example, language 1 as domain X, language 2 as domain Y. Then you can do unsupervised translation without pair data. This is what Facebook do. So this is their result. I'm not going to go through the detail of the technology they use. I just want to show the result. Here the result is those curves are from supervised learning. So they translate different languages. Those curves are from supervised learning. Then those horizontal lines are from unsupervised learning. And you can find that unsupervised learning obtain the same performance with 100K sentence pair. So if you have data less than 100K sentence pair, unsupervised learning can even achieve better performance than supervised learning. For part 2, we are really running out of the time, so we just give you some highlight about what you can achieve. So for GAN, you can use GAN in speech enhancement. For speech enhancement, what you want to do is you input a noisy speech. After a network, you obtain clean speech. It can be considered as a supervised learning task. You collect some noisy speech and its corresponding clean speech and train a network, input the noisy speech, output the clean speech. Then, of course, you can use the conditional GAN on speech enhancement. You learn a generator, input noisy speech, output clean speech, and you learn a discriminator. Its input is the input of the discriminator is the input and output of the generator to check that whether this 2 is a pair and whether this 1 is a clean speech. And the algorithm is exactly the same as conditional GAN. And there are lots of research. Unfortunately, no one has strong evidence that this approach is better than the previous deep learning based approach. Speech enhancement have been widely studied, and there are lots of very strong deep learning based approach. And until now, no one can show that speech enhancement by GAN is better than those approach, just comparable. And of course, you can do speech synthesis, and I do not have to describe. You can generate image, so you can generate speech just like generate image. So that's it. Then for voice conversion is not new for people because in Conan, 20 years before, he is already very successful. However, there is already very successful. But in the past, when you want to do voice conversion to transform the audio of speaker A to speaker B, you need pair data. You need speaker A and speaker B say the same thing. So A say, how are you? B also say, how are you? Then you can train a network to transform the audio of speaker A into speaker B by supervised learning. So this is nothing special. Lots of people working on that. But this is the past. Now with GAN, you only have to collect the audio of speaker A and audio of speaker B. They do not have to be paired. And they don't even have to be speak in the same language. You can transform between speaker A and speaker B. So the idea is very simple. This is CycleGAN. You can transform image in X domain into Y domain. Just consider the audio of speaker A as X domain, audio of speaker B as Y domain. Then that's it. You apply just apply CycleGAN and to transform the audio from speaker A to speaker B. This is the result. So the figure looks complicated. So in a nutshell, for similarity, the proposed approach is not this CycleGAN approach is not good enough. And we will deal with this problem in the last part. For speech recognition, you can apply domain adversarial training to improve your speech recognizer. You can consider different accent as different domain or different noise condition as different domain, and just simply use the domain adversarial training technology. You can get some improvement from the literature. So you can check the slide by yourself. So let's probably take probably 5 minutes break. So then we will talking about part 3.